Every time you click Power On in VMware, ESXi silently launches an entire computer from scratch in just seconds. Most VMware admins know how to power on a VM, but very few understand what actually happens inside ESXi after that click. Behind this simple action, ESXi starts multiple internal processes, allocates resources, creates virtual hardware, maps memory, schedules CPUs, and finally boots an operating system. In this video, we'll break down the complete internal VM power-on workflow step by step, exactly the way enterprise architects and VMware engineers think about it. So let's start with the first question. Why does understanding this process even matter? Understanding VM power-on internally can completely change how you troubleshoot VMware. This topic is extremely important in real enterprise environments. When a VM fails to boot during production outages, HA events, or disaster recovery situations, understanding the internal workflow helps you identify exactly where things failed. It also explains performance bottlenecks, resource contention, and many VMware interview questions that confuse professionals. And honestly, concepts like VMX, worlds, and vMkernel are often misunderstood even by experienced admins. So now let's zoom out and look at the complete high-level workflow first. A VM power-on is not one action. It's an orchestration pipeline. When the user clicks Power On, vCenter sends a request to the ESXi host. ESXi validates the VM configuration, creates the VMX process, allocates CPU, memory, storage, and networking resources, initializes virtual hardware, starts BIOS or UEFI, and finally boots the guest operating system. What looks like a simple button click is actually multiple ESXi subsystems working together in perfect coordination. So where does this entire process actually begin? vCenter looks powerful, but it doesn't actually power on the VM itself. The process starts when a user clicks Power On from vSphere client, Power CLI, API calls, or automation tools. vCenter then sends an API request to the target ESXi host. Inside the host, services like Hosted and the vpxa agent receive and process the request. This is important to understand. vCenter is mainly the management layer. The actual execution happens inside ESXi. Once ESXi receives the request, the first thing it does is validation. Before ESXi powers on anything, it verifies everything. ESXi checks the VMX configuration file, virtual disks, snapshot integrity, data store accessibility, permissions, and resource availability. It also verifies CPU, memory, networking, and storage connectivity. If even one validation fails, the VM power-on stops immediately. This is why issues like file locks, corrupted snapshots, or insufficient resources can completely block VM startup. After validation succeeds, ESXi creates the most important process of the entire VM. This is where the VM actually starts becoming alive. ESXi now creates the VMX process, the main user world process of the virtual machine. You can think of VMX as the brain of the VM. It manages virtual hardware, handles device emulation, coordinates VM lifecycle operations, and communicates directly with vMkernel. Every powered-on VM inside ESXi has its own dedicated VMX process. But the VM still doesn't have resources yet, so next, vMkernel steps in. Now, ESXi begins reserving real physical resources for the VM. vMkernel allocates CPU, memory, storage, and networking resources. The scheduler creates vCPU worlds, helper worlds, and device worlds. Memory gets mapped and tracked, NUMA optimization may occur, and storage paths are initialized with VMFS locking. This is the stage where the hypervisor prepares the environment required for the VM to actually run. And this introduces one of the most misunderstood VMware concepts: worlds. A virtual machine is not a single process inside ESXi. In ESXi, execution happens through entities called worlds. There are vCPU worlds, VMX worlds, MKS worlds, and device worlds. These are lightweight execution contexts managed by vMkernel. Understanding worlds is extremely important for performance troubleshooting because tools like ESXtop, vSISH, and vMkernel logs expose VM activity through these worlds. Now that execution contexts exist, ESXi begins creating virtual hardware. This is where ESXi starts building a virtual computer. ESXi creates virtual CPUs, RAM, BIOS or UEFI firmware, virtual NICs, SCSI controllers, and virtual disks. Then device emulation begins. The guest operating system doesn't directly see the physical server hardware. Instead, it sees standardized virtual hardware presented by ESXi. Now comes one of the most advanced parts of virtualization engineering: memory virtualization. Memory virtualization is one of ESXi's greatest engineering achievements. ESXi maps guest virtual memory to guest physical memory, and finally to host physical memory. vMkernel uses technologies like hardware-assisted MMU, Intel EPT, and AMD RVI for efficient memory translation. It also uses optimization techniques like ballooning, transparent page sharing, compression, and swapping when required. This entire abstraction layer allows multiple VMs to efficiently share physical memory resources. After memory is ready, ESXi starts virtualizing CPU execution. A vCPU is not the same thing as a physical CPU core. vMkernel's CPU scheduler now maps vCPUs onto physical cores. The hypervisor handles context switching, time slicing, CPU fairness, and NUMA awareness to balance workloads efficiently. This allows many virtual CPUs across multiple VMs to share limited physical CPU resources while maintaining performance and isolation. Now the VM finally starts behaving like a real physical server. At this point, the VM thinks it's a real physical machine. The virtual BIOS or UEFI initializes, hardware inventory is detected, and the boot order is checked. Then the bootloader starts. The guest operating system kernel loads into memory, and operating system initialization begins. Finally, the VM becomes fully operational. But what happens when this process breaks? Most VM boot failures can be traced back to one failed stage. Failures can happen during VMX startup, data store locking, snapshot validation, memory allocation, or network initialization. That's why VMware troubleshooting heavily depends on logs like vmware.log, hostd.log, and vmkernel.log. Once you understand the internal power-on sequence, troubleshooting becomes far more logical and much faster. And behind all this, multiple ESXi components are working together simultaneously. VM power-on is actually distributed orchestration inside ESXi. Multiple ESXi components participate during VM startup. vMkernel handles core resource management, VMX manages virtual hardware, hostd and vpxa process requests. Schedulers, memory managers, storage stacks, and networking stacks all coordinate together. This is why VMware architecture is so powerful at enterprise scale. Now, let's see how this knowledge becomes critical in real production environments. This entire workflow becomes critical during HA failovers. When a host crashes, VMware HA detects the failure and selects another ESXi host. The VM gets registered again, and the complete VM power-on workflow restarts from scratch on the new host. This explains HA delays, boot storms, resource contention, and restart prioritization during enterprise outages. And this is exactly why VMware interviewers love asking these questions. These are some of the most commonly misunderstood VMware interview questions. Interviewers often ask, what is VMX? What are worlds? How does ESXi virtualize CPU and memory? What happens internally during VM power-on? The goal is not memorization. They want to see if you understand the architecture, components, and workflow behind virtualization. So let's summarize the complete architecture one final time. One click triggers an entire hypervisor orchestration pipeline. The workflow starts with the user and vCenter, moves through host D and VMX, enters VMkernel for resource allocation, initializes virtual hardware, starts BIOS or UEFI, and finally boots the guest operating system. So the next time you click Power On in VMware, remember, ESXi is launching an entire virtual computer from scratch in seconds. And if you found this deep dive useful, most people use virtualization every day, but very few understand what's happening underneath. If you enjoyed this VMware deep dive, subscribe for more enterprise architecture breakdowns and real-world VMware internals. Also, comment below with the most confusing VMware topic you want explained next. And for the next video, we'll go even deeper. What actually happens during vMotion? Keep learning, keep building, and keep thinking beyond the GUI.